Have you ever made a spectacularly bad decision? And I mean really bad. Not because your execution of a plan was flawed, but because, well, your mental model of this situation was just completely outdated.
Oh, yeah, like you're operating on old software, basically.
Exactly. Like, imagine you are navigating a city using a mental map from, I don't know, 10 years ago,
Mm.
and you make this flawless, highly confident left turn directly into a brand new brick wall.
Right, because the city rerouted the traffic patterns while you weren't looking.
Yes, your actions, your driving, it was perfect.
Yeah.
But your internal imagination of the outcome was fundamentally broken.
I mean, you relied on a static model in a dynamic world, right? Which honestly is the exact bottleneck that is currently suffocating artificial intelligence.
So today we are dismantling that bottleneck.
Oh,
Welcome to the deep dive. We are looking into a really fascinating new ArcSieve paper. This is from June 2026, and it's titled COMAP, Co-Evolving World Models and Agent Policies for LLM Agents.
it's a mouthful, but it's a huge deal.
It really is. Our mission for this deep dive is to explore how researchers are finally teaching AI agents to constantly update their own imagination of the future, essentially stopping these systems from driving into those metaphorical brick walls.
Yeah, because it represents a profound shift in machine intelligence. I mean, the industry is just hitting a massive ceiling with static training right now and transitioning towards systems that continuously adapt their own internal foresight. It's not just a cool trick anymore. It's becoming mandatory for complex tasks.
Right, so to really wrap our heads around the mechanics here, we have to look at the two architectural pillars of an LLM agent that they talk about in the paper.
The nuts and bolts of it.
Exactly. First, we have the agent policy. This is the part of the system that acts as the driver. It looks at the current state of a task like navigating a web browser or using API tools, and it makes the active choice of what to do next.
Right, it's the action taker.
Yeah. And then second, we have the textual world model. So if the policy is the driver, the world model is the GPS look-ahead system on the dashboard. It simulates the consequence of an action before the agent actually takes it.
Which is crucial, right? The world model provides this in-context information in the form of predicted future states. It essentially gives the agent the ability to pause, take a breath, and imagine the downstream effects of its actions.
Okay, but I look at that setup and I just wonder, why can't we simply train the driver better?
How do you mean?
Well, if the AI is failing at long horizon tasks, the standard engineering impulse is to just, use reinforcement learning, give it external rewards, or maybe write better human-guided rubrics to improve the agent policy itself. Fiddling with the internal GPS just seems like we're overcomplicating the whole architecture.
What's fascinating here is a statistical concept known as a non-stationary distribution.
Okay, non-stationary distribution. Let's break that down.
Right, so complex digital environments are not static puzzles. As you train an agent policy, it actually becomes more capable over time. It abandons simple, repetitive actions and starts exploring these highly complex strategies. It pushes into entirely new subspaces of the environment that it has quite literally never encountered before.
So it navigates off the standard highway and starts taking intricate, completely undocumented back roads.
Exactly. And if the world model's training was frozen before deployment, which is how it's usually done, it has zero data on those back roads.
It's flying blind.
Completely. So when the evolving agent queries the world model about, say, a complex new API call, the static model is suddenly forced into an out-of-distribution prediction. It gives poorly calibrated, just highly inaccurate feedback.
Because it's trying to guess based on an outdated map.
Yes, it actually hallucinates a successful consequence because it just fundamentally doesn't understand the novel error states that the smarter policy just uncovered.
Oh, wow. So the agent trusts that hallucinated green light, executes the action, and just crashes the whole task. The static map is actively sabotaging the smarter driver.
And the dynamic also works in reverse.
Wait, really? How so?
Well, think about a weak, newly initialized agent policy. It only takes basic, uninformative actions. If you try to train a world model on that baseline data, the model starves.
Because it's not seeing anything interesting.
Exactly. It overfits to a tiny, boring slice of the state space because it never gets to observe diverse, complex environmental transitions.
Okay, so improving either component in isolation is just structurally doomed. A bad driver starves the GPS of varied routes, and a static GPS feeds a good driver terrible directions.
You nailed it. And that explains why current state-of-the-art methods eventually plateau when they try to solve these long-horizon interactive tasks.
Okay, let's unpack this. Because the paper's proposed solution naturally stems from that exact bottleneck. If they must evolve, they have to evolve together.
Hence the name of the paper.
Right? COMAP,
Mm-hmm.
which stands for Co-Evolving World Models and Agent Policies. The researchers built this closed, mutually reinforcing loop. They call it the decision loop.
And it's a really elegant workflow.
It is. Rather than just acting immediately,
Mm.
the agent drafts a candidate action, but it holds off on executing it. It hands that draft over to the world model, and the world model performs a textual look-ahead, yielding feedback on the likely consequence.
And the critical step happens right after that. The agent receives that imagined consequence and performs what they call future-aware reflection.
Meaning it doesn't just blindly accept the prediction.
Exactly. It estimates the reliability of that feedback and actually uses it to refine its action. It's effectively editing its own behavior based on a simulated future well before it interacts with the real environment.
That is wild.
Yeah, and if we connect this to the bigger picture, this mutually reinforcing cycle is exactly what shatters those previous performance ceilings.
Because they're talking to each other.
Right. As the policy improves through this continuous reflection, it successfully navigates into much deeper, more complex environmental states. And those complex states generate fresh, high-quality on-policy trajectories.
Which are then immediately fed back into the world model to update its map.
Precisely.
So the fresh data forces the world model to provide more faithful future predictions, which in turn guides the agent to make even more sophisticated long-horizon decisions. You know what it mirrors? It mirrors a chess player developing their internal mental simulator over time.
That's a great way to think about it.
Like a novice looks at the board and can barely simulate one move ahead.
Yeah.
Their internal model is basic because their skill is basic.
But as the player learns advanced tactics, their internal simulator is forced to adapt. It starts modeling 6 or 7 moves deep, anticipating complex board states that a novice couldn't even conceptualize. The player's skill and their internal simulator are inextricably linked.
Here's where it gets really interesting, though. Because the theoretical beauty of a closed loop often masks a massive engineering vulnerability.
The echo chamber problem.
Exactly. A self-feeding loop introduces a severe risk of an echo chamber. I mean, if the world model's early predictions are garbage, the agent is going to reflect on hallucinated data, right? Make terrible refinements, and then generate even worse data for the next cycle.
It's a cascading failure.
Yeah, the system should mathematically collapse under the weight of its own noise.
And it absolutely would. That is the primary failure mode of self-improving systems. Noise amplification.
So how did they fix it?
Well, to prevent the loop from collapsing into an echo chamber of bad predictions, the researchers didn't just turn the loop on and walk away. They engineered 3 highly controlled training phases.
Okay, let's go through them.
The first is initialized training, which is effectively a warm-up phase.
Meaning you give the system a baseline using expert demonstrations and real environmental rollouts. You kind of ground the initial distribution so the AI's first guesses aren't just pure statistical noise.
Exactly. You provide a foundational understanding of the environment's causal physics. But, a baseline is just a starting point. The core engine of the system lies in the second phase, which they call on-policy self-distillation.
Okay, self-distillation.
Yeah, this is where the world model actually learns from the agent's exploration on the fly. During training, the world model architecture is split into 2 modes, a teacher mode and a student mode.
And the teacher mode is given privileged access to the environment, right?
Correct. When the agent takes an action, the teacher gets to see the actual ground truth state transition that occurs in the environment.
So the teacher knows the reality.
Right. But the student mode is flying blind. It only sees the current state and the proposed action, and it has to predict the outcome.
Okay, I see where this is going.
So the system calculates the token-level divergence between the student's prediction and the teacher's privileged knowledge, and it trains the student to minimize that divergence.
Oh, wow. So you are mathematically forcing the student's internal semantic representations to align with the actual causal dynamics of the environment. The teacher literally has the answer key and pulls the student, token by token, away from hallucination and toward reality.
That's a perfect summary, yeah.
But wait, even with distillation, the student model is still going to produce flawed predictions early in the training cycle, right? Like, it's learning. If the agent's future-aware reflection uses those flawed predictions, don't we still hit the echo chamber problem?
We do, which necessitates the third phase, the gates.
Ah, okay. The gates.
Yeah, the researchers implemented two gating mechanisms to carefully control the flow of information and protect the policy from early world model noise. The first is the action gate.
Okay, what does that do?
After the agent performs its reflection and generates a refined action, the action gate evaluates the refinement against the original draft.
To make sure it didn't just make it worse.
Exactly. It prevents the agent from overthinking and discarding a perfectly optimal initial strategy just because the reflection process introduced some unnecessary complexity.
That makes total sense.
And then the second, which is far more critical for the training phase, is the world state gate.
Right, the world state gate.
During the loop, this gate decides the origin of the future state that the agent uses for reflection. It actively chooses whether to feed the agent the actual next state directly from the environment or the predicted next state generated by the student world model.
And the researchers didn't just leave this as a basic binary toggle, right?
No, not at all.
They identified a specific adoption threshold for the world state gate, setting the hyperparameter at top 0.6 second.
Right, point 0.6. That threshold dictates the entire curriculum learning schedule. It is a mathematical forcing function that balances exploration against the risk of noise collapse.
Because if the gate relies entirely on the real environmental state, the agent never learns to trust its own internal imagination.
Exactly. It becomes completely dependent on external feedback, which, by the way, it won't have during actual deployment.
Right. But if it relies entirely on the predictions early on, the noise compounds. So
Yeah.
a threshold of 0.6 creates this dynamic safety net.
Yeah. Early in the training cycle, the world model's confidence is low, and its predictions often fail to meet that 0.6 threshold. So the gate is conservative. It defaults to the real environment to keep the agent grounded in factual cause and effect.
But as the self-distillation phase improves the world model's accuracy, its predictions begin crossing that 0.6 threshold more and more frequently.
Exactly. The gate slowly shifts the balance, gradually exposing the agent policy to its own internal guidance.
It is an incredibly elegant way to take the training wheels off at the exact rate the system builds its own competence.
It really is beautiful engineering.
Okay, but all this elegant engineering sounds compelling on an architecture diagram, but I'm a bit skeptical of theoretical models until they are truly stress tested. I mean, we need to know if this closed loop actually outperforms standard massive models that rely purely on scale. Let's look at the benchmarks.
Let's do it. So the researchers subjected COMAP to 4 highly rigorous, distinct environments.
And these aren't easy tests.
No. First is ALF World, which evaluates household planning tasks requiring spatial reasoning.
Right.
Then Science World, which demands multi-step scientific methodology. Web Shop, which tests the agent's ability to navigate complex e-commerce interfaces. And finally, Stable Toolbench, testing the execution of highly intricate API toolchains.
The performance leaps on the open-source trainable backbones are honestly staggering. Let's isolate the Qwen34B model. For a relatively small 4 billion parameter model, implementing the COMAP framework yielded a 16.75% relative improvement in task success rate compared to the standard ITPR baseline.
That's a massive jump.
It went from an average 51.52% success rate to 60.15%.
And extracting that level of reasoning from a 4 billion parameter architecture really proves something. It proves that outfitting a smaller neural network with a continuously updating internal simulator aggressively compensates for a lack of raw parameter density.
Yeah, but the data point that completely disrupts the current paradigm happened with the larger Qwen38B model.
Oh, this is my favorite part.
Running the COMAP framework, that 8 billion parameter open source model actually surpassed the performance of GPT-5.4 running with standard React prompting.
It's unbelievable.
An 8 billion parameter model outmaneuvered a massive proprietary behemoth simply because it possessed a co-evolving imagination.
It absolutely forces a reevaluation of how we allocate compute. Scaling parameters is not the only path to advanced reasoning. Architectural methodology can clearly punch significantly above its weight class.
Okay, but playing devil's advocate here, success rate alone feels like a blunt instrument.
Fair point.
Like, an agent could theoretically brute force its way to a higher success rate without actually understanding the environment. We need a metric that proves the internal simulator is accurately mapping reality, rather than just generating plausible-sounding text that happens to align with a successful action.
Right. And standard text generation metrics like BLEU or Rouge completely fail here.
Because they only measure surface-level word overlap, right?
Exactly. So the researchers utilize a metric called delta F1, and this isolates whether the world model accurately predicts the specific action-induced state changes using canonicalized facts.
Canonicalized facts. Let me give an example to make sure I'm getting this. So if the agent is navigating a kitchen environment and executes the action turn on the faucet, the delta F1 metric strips away all the semantic dressing.
Right, it ignores the fluff.
It doesn't care if the world model writes a beautiful descriptive paragraph about the water flowing. It just parses the prediction to check if the underlying logical facts changed. Like, did the status of the faucet change from off to on, and is the sink now categorized as wet?
Exactly. It evaluates pure causal reasoning, and across the benchmarks, COMAP achieved a 90.29% average delta F1 score on the Quen 38B model.
Wow. Over 90%.
Yeah. The precision of its internal imagination is incredibly robust. But, this raises an important question. What happens if we actively dismantle the framework?
The ablation studies. This
Right.
is where the necessity of the coevolution is irrefutably proven, right?
Absolutely. They surgically removed components of COMAP to see exactly where the system bleeds.
Okay, what did they find?
Well, they took the fully operational 8 billion parameter model and simply froze the world model after the initial warm-up phase. So they kept the future-aware reflection active, but stopped the world model from co-evolving with the policy.
They basically turned off the GPS updates while the driver kept learning.
Yes. And the delta F1 score plummeted by 29.1%.
Oh my God.
Yeah. Without the continuous updates from the agent's new trajectories, the static model immediately misaligned with the environment.
It broke instantly.
And furthermore, when they removed the predicted future state input entirely, basically stripping the agent of its ability to reflect before acting, the overall task success rate dropped by 24.1%.
So the agent cannot maintain high-level performance without its imagination, and that imagination collapses if it isn't constantly fed by the agent's actions. The mutual dependency is absolute.
Completely absolute.
What about the self-distillation phase? Did the teacher-student token divergence minimization actually outperform standard training?
Decisively. They compared their on-policy self-distillation against standard off-policy fine-tuning, measuring what's called the change token negative log likelihood.
Which evaluates how difficult it is for the model to predict the specific tokens representing an environmental state change.
Right. A lower score means higher accuracy and confidence. Standard fine-tuning resulted in a 1.80, but COMAP self-distillation brought that down to 1.38.
That is a massive reduction in predictive friction. It really validates that the teacher-student closed loop captures the nuances of causal changes infinitely better than just force-feeding an AI static datasets.
It's just a smarter way to learn.
So what does this all mean? We are looking at a fundamental architectural pivot in artificial intelligence. Building smarter, highly capable autonomous agents is no longer just a brute force exercise in scaling parameters or expanding static data sets or writing increasingly convoluted prompt engineering rules.
No, it requires an internal ecosystem.
Yes, true autonomy requires engineering and architecture where an agent's imagination of the future and its decision-making policy are locked in a continuous loop, teaching each other without human intervention.
It elevates the AI from merely memorizing an environment to actively learning how to navigate the underlying mechanics of cause and effect. It adapts its own worldview based on the expanding horizon of its own capabilities.
And it achieves this with ruthless efficiency, allowing an 8 billion parameter model to legitimately compete with the most resource-intensive models on the market.
It's a huge step forward.
It is. But I want to leave you with a final provocative thought to mull over, one that stretches the implications of this research into far more dangerous territory. The researchers explicitly note a current limitation. The COMAP framework has only been tested and validated in text-based environments. Navigating a web browser or sorting files with an API are complex tasks, sure, but they are sterile.
Right, there are clear rules.
Exactly. So if we attempt to scale this coevolution framework into the physical world via embodied robotics, where visual, spatial, and auditory data are infinitely messier, continuous, and subject to real-world physics, could an AI's internal imagination safely keep up with the chaos?
That is the million-dollar question.
In a text environment, a hallucinated prediction just results in a failed web query. In the physical realm, could slight, compounding hallucinations in a robot's visual world model lead to catastrophic, irreversible physical actions before the closed-loop system even has the computational time to recognize the error and correct its course.
The leap from discrete text tokens to continuous physical space is the ultimate frontier. The stakes for maintaining accurate, real-time coevolution become astronomically higher when an out-of-distribution prediction means a robotic arm driving itself straight through a solid table.
Exactly. We have successfully engineered a way to stop an AI from driving into a metaphorical brick wall by giving it a continuously evolving map. The next monumental challenge is guaranteeing it doesn't drive into a real one.